Welcome to the second AI session. This one is going to be on supervised learning, and we're going to be exploring classification and regression algorithms. It's probably going to be a long one, but tomorrow is probably going to be a shorter one. And for that reason, if at any point you have any questions, feel free to interrupt it. Yeah. What's your question?
Can you share the slides further?
It's the same slides I shared yesterday, so everything is going to be there eventually. But you just have to look up these slides. Should be slide 21 or 20, whatever. All right. So yeah, feel free to ask any questions. We can also make these a little bit interactive. Like if there's any step in the logic that's not super clear, let me know, and I can explain it on the whiteboard or give some more examples. But yeah, and tomorrow we're probably going to do a shorter class on supervised learning, and then at the end you'll have the chance to try out for the first time some of these algorithms. So it's easy to set up an environment on Google Colab, which is a platform that you can use to run Python there and test all these algorithms. So yeah, looking forward for tomorrow, so you can try out the algorithms for the first time. All right, so the simplest algorithm when it comes to regression is linear regression, and you might have already heard about it. Probably in the context of just a function of one variable to one variable. So if you have your y and your x, and you have data points somewhere, and this could be like x is your the number of square meters in your house, and y is like the price. The simplest model that you can train on this data would be like a linear regression of one variable to one variable. So you'd feed a line like that goes through the data as best as possible. And the goal with linear regression is to minimize all the errors, or in this case, the squared errors. So you calculate all the differences to the line, and you take all of these differences in the y-axis, so it's like the error in the output. You square them and you sum them together, and you try to find a line that minimizes this. So if you had, for example, a line that went over here, all these errors would be way larger, and so that's not the optimal line. What you want is the line that minimizes all of these errors. So you might have come across this example, but in fact, linear regression doesn't need to be just one variable to one variable. In this case, you have two variables, so x1 and x2. And your output will still be one variable. And you can still train a linear regression algorithm in order to feed this data, and the principle is exactly the same. So you try to find, in this case, a plane that minimizes the errors for each of your data points. And so in this case, you have like a data set where you have several points. Each point has a y and can have multiple x's, in this case, 2, and you try to find a model which will be the output equaling a certain term called beta 0, which would be the intercept on the y-axis, and then several terms where you multiply each of your inputs by a given weight. And so your goal here is to find all of the betas that will give you a plane that minimizes this error. If you have several examples, you can use linear algebra or like matrix notation in order to express this in a much simpler form. So you can just say y equals x beta plus your error, which you're trying to minimize. And in which case, y is a vector with all of your outputs. X would be a matrix where in the first column you're going to have only ones. So when you multiply this matrix by this vector, you're going to have only beta 0 and no x there. So it's just beta 0 times 1. And then all of the other columns will be all of your inputs for all of the samples. So you're going to have each column is going to be an input, and each row is going to be a sample. And so when you multiply these with beta, you're going to have, I'm assuming you're more or less familiar to how like matrix multiplication works, right? Is there anyone that, no? Okay. Okay, in that case I'll explain to you. Yeah, but that's actually great. Anytime I start explaining something and it's not making a lot of sense, it's probably because I'm assuming there's some background knowledge, and if it isn't there, or anytime it doesn't make sense to you, just let me know. So the way you do this multiplication of x times beta, let's do a simpler example. So let's say you have a 2 by 2 matrix, and let's say your values are like 1, 2, 3, 4. And let's say you want to multiply this by a certain vector. And let's say this is like 5, 6, whatever. The way you multiply two matrices together, or a matrix and a vector, is that on the left side, you take the first row, and you're going to combine it with the first column on this right side. So in this case, it's 1 times 5 plus 2 times 6. So you're going to have something like 1 times 5 plus 2 times 6. And that's going to be the first element on your output vector. And then the second element, you're going to take the second row, and in this case multiply it again with the first column, and that's going to give you the second row, first column of this output. So in this case, it's going to be 3 times 5 plus 4 times 6. And then you can do the math and get the final result. Let's just do it for completeness. So this will be 17. And that will be 39. Thank you. Yeah, let's make this as interactive as possible, please. All right, so that's how you multiply two matrices, or in this case a matrix and a vector. But if you had some more elements, if this was another matrix, you just have a second column here, and you will do the same process, but for this column, and that will give you the result for this column, and in this case you'd have a 2 by 2 output matrix. But that's how you multiply a matrix by a vector. And so in this case you do the same thing with x and beta. And if you carry out this process, you're going to get this, exactly. And at the end you also have epsilon, which is going to be 1 per element. And so this will be the formula for one single sample. So it's going to be y1, for example, let's say I equals 1. y1 is going to be this row multiplied by all of the betas. So in this case, beta 0 times 1 is going to be beta 0. Beta 1 times x11 is going to be beta 1 x11. And so on. If you go through all of the rows, you're going to get this expression. And then you have an epsilon at the end, so you just add epsilon 1, and that's it. So actually, these two formulas are exactly the same. And so your goal here is essentially to find what are your betas, your beta vector, that will minimize all of the squared errors, or the sum of squared errors. So the way you express this, like here on the top, is basically the same thing as we had before. And the x times beta minus y is just your epsilon. You can just switch the x beta to the other side. And or you're going to have minus epsilon, but it's the same because you're taking like the modulus here. So this is actually, can you see the, yeah, perfect, you can see the mouse. Okay, so this would be like minus epsilon, but the squared magnitude of epsilon is going to be, doesn't matter if there's a minus there. So this will be your loss. This is what you're trying to minimize. And you can do like some algebra. I'm not going to explain this completely, but you can do some algebra to express this in terms of all of the y's, x's, and betas. And these are all like matrix multiplications. And since you want to minimize this loss, what you do is you take the derivative of the loss with respect to the betas. And so if you take a derivative, so derivative is like, you have a certain function, and let's say it does this. The derivative would always be like the slope at each point. So in this case, it would be positive, because the function is going up. But for example, in this case, it would be negative, because the function is going down. Oh, wait, not like this, but maybe let's do it, yeah, like this. And so if you want to find the minimum of a function, which that's what we're trying to do with the loss function, you want to find the minimum of this function is always going to be a point where the derivative is 0. So this is what we want to find. And so we take the derivative of this big expression with respect to beta. Here we're skipping the step of like actually computing or like deriving this derivative. You just get the result. And then you set that derivative equal to 0, like here at the bottom. And so if you then solve for beta, you're going to have the beta vector that minimizes your loss. And so if you then plug this beta back into the model here, that's this, like the relationship between y and x is going to be exactly what you have on this plane. So you solved the problem of like finding this plane that minimizes the errors. And so then you can like try to evaluate like how good is your solution. So what we use here is this r-squared metric, and that is basically it's just a function of how much of the squared error you can explain as a ratio of the total squared error if you assume your function is just a single value. Let me explain that. So what this r-squared term is just 1 minus this fraction. And what this fraction is, on the top you have y minus y hat, where y hat is your prediction. And so this is exactly all the squared errors that we see there. So same as we've done before. So you have a bunch of points, you have a line that goes through them. Like the first or the top term, which is squared sum of squared residuals. The residuals are just these lines. So you just sum the square of all of these lines together. And the bottom term is sum of squares total. And you see that it's almost the same thing, but instead of your prediction, so instead of the straight line, you just use the average of the points, the average y. So in this case, the average y of all these points would be somewhere along here. So this would be y average. And you can imagine you have a different model that predicts just the average, and you look at the residuals with respect to this average. And that's going to give you your sum of squares total. And so your r-squared term is just 1 minus this ratio. So you can try out a few things. So, for example, if your model just predicted this average, what would this look like? What would be r, or r squared in this case? Sorry?
What the question, sorry?
So let's say you have a model that just predicts the average of all of the outputs. What would be r squared?
R squared.
All the outputs were on the line.
Sorry?
All the outputs were on the line. Is that what you said?
So your model just predicts the average of all the y's.
Standard deviation.
That would be, it would, like the sum of squared errors would be the variance, which is the square of the standard deviation.
2.5.
Sorry?
0.5.
1.5?
No, just 0.5.
0.5? Why is that?
It's the average that's going through.
Yeah, but we're also dividing like by the average, so. Who said 1? Yeah, exactly. So if your model predicts exactly these residuals, you're just going to be dividing the S total divided by the S total. And so this term would be 1, and so r squared would be 0. Okay. And so this is like kind of a baseline. Like whenever you're trying to predict something, like the best or the baseline case would be just trying to predict the average. But in that case, you have a r squared of 0. But if instead you have like your linear regression fitted nicely, your error terms are going to be much smaller than before. And so you're going to have an r squared value. So this here is going to be a term that's less than 1. And so r squared is going to be somewhere between 0 and 1. And now let's say we have an example where actually all of the points lie in a straight line, and you are able to perfectly fit them. So what would be r squared in that case? So r squared would be 1 because this on the top, all of these errors would be 0. So all of these would be 0, and so r squared is 1, and that's basically the best you can get in terms of regression. So r squared is basically just a metric that tells you how good your regression algorithm is. And you can use it to like, once you have more complicated, you're trying to do like some kind of nonlinear regression. Although this r squared term is mostly used for linear regression. But you can use it to compare different models, for example. So this seems fine, but actually linear regression, as simple as it is, also still has a few problems. So one of them is if you have correlated inputs. So for example, your inputs here would be age and experience, and you can kind of understand that this would be very much correlated because age increases or experience increases with your age. So all of the points are going to be lying on a straight line. And if you try to fit a plane to a straight line, there's actually multiple solutions, right? So you could have this plane, but you could actually rotate it around the points, and it would still be a valid solution. And so in the end, you can end up creating models that are going to explain the data in a very weird and non-robust way. So usually when we're talking about regression models, we want to have them like actually explain the mechanisms, or as best as possible in a robust way, the data that they're trying to fit. And another problem is also that if you have a lot of inputs in respect or versus the number of samples that you have, for example, this is a data set of house prices, and you can have like several input variables for this. I have them here. They're kind of too small, but you can kind of look at them in your computers. It can be anything from the age of the property, the tax value, the level of nitric oxides, for example, whatever. So you can throw anything at your model, but if you have too many inputs, a lot of them are going to be producing just noise in your model. So you might not want to have a model that takes all of them into account. but you still want to have a model, but you don't know a priori which ones are going to be useful or not. So it would be nice to have a technique that would actually select which input variables you want to use in your model, and then be completely robust to any kind of noise in the other ones. And so, yeah.
Can you have tolerance in these two kind of models, or you are eliminating with the polynomial?
There's kind of a certain tolerance built in because the model doesn't need to fit the points exactly. And so there's already some tolerance in the sense that the best fitting plane is going to have some errors. It might be possible, there might be some techniques to actually bound those errors, so find a model. But that would be expressed in terms of like constraints to your optimization. And in that case, you'd probably need a more complicated optimization process, but it is doable. And especially with like nonlinear models, you can introduce constraints on them and be able to fit a model that respects those constraints. Okay, so the way we can solve these two issues, like the correlated inputs and also the having too many input variables, is using something called regularization. So this is a term that you add to your loss function in order to have better properties in your output model. So here on the left, you see the sum of squared errors, as we saw before. That was our original loss. But now we can include a different term, and we weight it by a value called lambda that we can define anywhere. Usually it's like a small value, so we just add a little bit of regularization, and that gives us some nicer properties on our final model. And this regularization is essentially just putting a penalty on the magnitude of your weights. So in this case, it's W here, but you can think of W as the betas from the previous example. It's just a different notation, but it means the same thing. And so you put a penalty on how large your weights are, and the larger they are, the bigger this penalty is going to be. And you can also choose different kinds of penalties. So one of them is L1 regularization, and we put a penalty on the actual magnitude of the weight, and it's L1 because the magnitude it's called the L1 norm. But you can also use L2 regularization, which uses an L2 norm, which would be just the squared of the magnitude of your weights. And so this gives us different shapes in our penalty. And these two types of regularization will have, or will introduce different properties. So here on the top we have again our sum, or residual sum of squared errors. And this is the same expression as we saw before for the loss when we expand it. And this expression it's called a quadratic form on beta. So this is basically a multivariate polynomial on beta. And so if you plot it in, it would be in 3D in this case. So you have two inputs, two betas and an output. It will give you this paraboloid shape because this is guaranteed to be convex. And so these lines here represent like the contours of these paraboloids. So if you slice this paraboloid at different heights, you're going to have these different contours which are going to be elliptical. And so by introducing this other penalty on the weights, in this case here, you have an L2 penalty. So it's going to be another paraboloid. And so this time, since it's symmetrical, it's going to be a circle. And it's centered at the origin because you're penalizing the magnitude of the weights. And so what you're trying to minimize is this term. So the solution to minimize this term on this paraboloid would be the center of it. So this would be the optimal weights. But since you introduced this constraint, the optimal weights are actually going to be shifted towards the middle because you introduced the penalty on their magnitude. And depending on the type of penalty that you introduce, you can have different solutions. So the L2 penalty, which is the square term, is going to give you a circular contour. And so you're going to end up having weights that have the smallest total magnitude possible. As this circle is going to end up being the smallest possible. But if you have the other type of regularization, so which was this L1 regularization, the contours are actually rotated squares. And so if you do the same analysis on them, what you end up having is that your final beta, the optimal weights for your model, are actually going to tend to end up in one of the axes because of these cross sections, or because of these contours. And so what this ends up meaning is that your final output is going to have some of the betas equaling 0. And so this means that some of your input variables are not going to have any effect on the model because they just get multiplied by a 0. Does this make sense? Kind of. Which part is confusing?
Can you explain the penalty concept?
Sorry?
Can you explain a little bit more the penalty concept? Because I understand that the idea of this is to get closer to the truth, let's say.
Mm-hmm.
So when you say you have penalty, you are making things more sharp, or how does that translate?
So the goal of the penalty is to introduce this kind of shift in your final weights. Because, for example, if you have a lot of variables, a lot of them are going to have noise, which is meaningless. So you don't want your model to learn this noise, and then once you try to predict something with your model, there might be a slightly different variable or value in one of the variables, and it's going to completely throw off your model because it's not robust to these meaningless variables. So introducing these penalties is one way to avoid these and to make your model more robust. Is that clear?
Clearer.
Sorry? Clear. We'll keep touching on these kind of issues with generalization throughout the lecture, so hopefully it will become clearer and clearer. But in any case, I'm also open if I can explain this in more detail maybe after the lecture. But hopefully you can get at least an intuition of what this is doing. But yeah, so let's keep going. So in this case, since this is not a straightforward optimization, we have several terms on it. What you end up having to do is use an optimization technique. So in these AI sessions, I'm not going to go too deep into optimization techniques, but one of the most common ones that we'll see for neural networks is called gradient descent, which I've talked about it yesterday, but it basically means that on your loss function, this will be a representation of your loss function. You just take the gradient everywhere, which is the direction where you increase the most the function, and you just go on the opposite direction. And so that just means that you try to go downhill all the time until you find a minimum. But there are some other ways to do this. And this involves using higher order derivatives. If you take a second derivative, it's instead of finding the plane that's tangential to your loss function, you try to fit a paraboloid to your function using the second derivative, and then you go to the minimum of that paraboloid, and you do this repeatedly, and you also end up in hopefully a global minimum. But these kind of techniques can also end up in local minima. Maybe I'll just touch on that briefly. So yeah, for example, here we saw that we can find here a global minimum, but there's other minimum that might not be global. So this would be like a local minimum because everything around it, the function is higher everywhere around it. But this would be a global minimum because it's lower than all the other points in the function. So there are some of the other optimization techniques here try to deal with this problem. For example, genetic algorithms deal with this problem. So the way genetic algorithms work is that you initialize a bunch of solutions in a lot of points, and you find the best ones, for example, this one, and you cross them, and you end up with a lower solution. So that's kind of a way to visualize genetic algorithms. But yeah, for these AI sessions, we'll mostly touch on this gradient descent technique. And this is what you end up using for this kind of regularization, either gradient descent or this. It's called a Newton solver, the one with a second order derivative. Okay, so we've learned about linear regression, but sometimes your data doesn't quite follow these linear relationships. For example, let's say you have your data set is just two variables. So your input variable is the number of hours you studied for an exam, and the output variable is just whether you passed or you didn't pass. So it can be just a 0 or 1. And what you try to predict is what's the probability of passing if you studied a certain number of hours. So for this kind of problem where you're trying to predict a probability, it's usual to use this algorithm called logistic regression. And this makes use of this function called logistic curve, and it can also be called a sigmoid function because of the S shape. And the formula for that function is basically what you see here. So it's 1 over 1 plus e to the minus x, or in this case z, whatever. I don't know a particular reason why this function in specific is used. But it's so common in the machine learning field that you'll see it all over the place in the next few lectures. It might come just from statistics, or it might just be like an hypothesis that we use. We kind of model that the probability is going to follow this distribution, and we just let that be. But it happens that this kind of sigmoid function models probabilities very well, and you can actually tune the algorithms to predict actual probabilities using these methods. But the way logistic regression works is you have this function, and then you put a linear model inside of this function. So in this case, it's you only have one variable, so you're going to have just a beta 0, which doesn't multiply with anything, and a beta 1 multiplying by your variable. And this is your final model. So your probability is going to be a function of x following this equation. And then it's just a matter of like solving for beta 1 or in beta 0, or in this case, solving it means optimizing for them. So trying to find the values where this probability matches with the actual output variables of whether you passed or not, as well as possible. And so before we were using that loss function of the sum of squared errors. But for this kind of algorithm, since we're using probabilities, and since our output is not a numerical value, it's 0 and 1, but this can be seen as a categorical value or a probability value, but in this case it's real events of whether we passed or not. It just takes the form of 0 or 1. But when we're dealing with probabilities, it's usual to use this kind of loss function, which is called the cross-entropy loss. And this function comes from statistics and also like information theory in general. And it comes from the concept of entropy of a certain distribution. And when you're like in information theory, you have this concept called like the callback library divergence, which is the divergence between two distributions. And so your output or your loss function, this cross entropy loss, is basically this callback library divergence. So you're trying to have the distribution of the probabilities of your output from your model to match as well as possible the distribution of the actual variable, output variable of whether you passed or not. And so in this case, this is the final loss function. And so the y here, the y's would be the actual values on your data set. So if you didn't pass, y is a 0. So you only take this term. And here pk would be the output of your model. So in this case, if y is a 0, you have this orange curve, which is just this logarithm of 1 minus p. And so you're trying to minimize that. And so you're trying to push your model to predict a 0. And when y is a 1, you get this logarithm of pk. And so if you try to minimize, actually, there might be a minus sign missing here. So if you try to minimize this, you're going to push your model to predict a 1 when yk is a 1. Yeah, there's a minus sign missing there because the logarithm of p should be something like this, actually.
P is smaller than 1, that's why it's like that.
P is smaller. Sorry?
P is smaller than 1, so that log is...
Should be negative. So with a minus sign, it becomes positive. I think that's it. When y is a 1. Yeah, exactly. That's it. So yeah, if you flip the sign of this, you get a negative log, which is what you should expect for values less than 1. And then the logarithm function just continues this way. But yeah, if you flip that, you just get this. So yeah, there's a minus sign missing there. Sorry. And so once again, the way you solve this is by using just an optimization solver. And you can also introduce those like L1 and L2 penalties here. And you like in terms of the choice of the solver, it's kind of up to you. Might depend on the data, might depend on which penalties you want to use, but you have several ones. And once you test this algorithm by yourselves, like the library has all of these implemented, so you just literally pass the string, the name of the solver to it, and it uses that solver. So you don't have to do much, and you can try a bunch of different ones and see which ones work the best for your data set. And yeah, so once you solve for beta 0 and beta 1, you should end up having a model that predicts the probabilities. This is still called the logistic regression because you're still trying to predict a certain value and not the actual class. You're not predicting 0 or 1. You're predicting a probability, a numerical value, so it's called regression. But you can very easily turn this into a classification algorithm just by introducing a threshold. So let's say if you fitted this model, and so it's fitted to the data, and then you want your model to actually predict the class or the actual y value, whether it's a 0 and a 1. You can just pick this threshold value and just say, whenever your model predicts something above the threshold, it's going to classify it as a 1. And whenever your model predicts something lower than your threshold, it's going to classify it as a 0. But then there's this choice of how do you pick the threshold value. And this is really up to you. depends on your problem. Usually if you apply this in a business setting, you should actually go to your boss and say, so what matters most? Do you care more about false negatives or false positives? So, for example, you can associate costs to these false negatives and false positives. You can even say, for example, let's say it's a COVID test, and you're trying to tune this COVID test and tune like its sensibility. So let's say you create a test that very often doesn't predict the person is sick when the person is actually sick. This might be very costly. So this false negative actually has a big cost around it. And let's say if the test actually predicts that the person is sick when it isn't, maybe there's not so much of a cost associated with that because just tell the person to do another one, for example. And so these false negatives and false positives might have different costs. And so it's kind of a business decision when you're applying this in a business setting to define which costs each of these errors have. And so based on those costs, that's how you define your threshold. So you can tune the sensibility of your algorithm so you actually have the most value out of it, or get the most value out of it. So I've talked about these like false negative rates and false positive rates, but you also have like a lot of other different metrics that you can use for your algorithm. I'm not going to explain all of them, but you can like look them up on Wikipedia or whatever. And it's all of these are essentially different metrics that you use to evaluate your algorithm. And the one you actually choose to make a decision on where to set the threshold value, that's kind of up to you. You should kind of try to understand them to figure out like when they're the most useful. But we won't do that here. I just want you to like know about this. So we've seen the first example of a classification algorithm. It's called logistic regression, but if you introduce the threshold, it's a logistic classifier. But you can have a lot of other classification algorithms. One of the simplest ones, it's this k-nearest neighbors algorithm, which I explained yesterday also. So essentially, this means that to classify a new instance or a new sample, you just look at the closest neighbors. In this case, k would be the number of neighbors the closest neighbors you look at. So for example, in the left here, you're looking at the three closest neighbors, so it's like k is equals to 3. And you just look at the most common class between those neighbors, and that's your output for your new sample. But then you have this question of how do I choose the value of k? And once again, the answer is kind of up to you. But usually what's done is that you try a few different values. And there's a few trade-offs in choosing a high k or a low value of k. So for example, if you just have k equals 1, you're going to be able to predict your input data or your training data perfectly. And you can think, oh yeah, this is great, 100% accuracy. But then maybe your test data it can have the same distribution, but the actual points might be in different places. And so if you have this very complex boundary, which you get when you have k equals 1, once you look at your test data might have like these negative samples somewhere here, for example, which is still part of the distribution, but then you will start having errors on them. Or for example, there might be this positive region here where you predict it as positive because there's a couple samples there, but in fact it's much more likely that you're going to have negative samples there. And so once you test this algorithm, it's going to have a lot worse performance than you'd expect. And so the way to solve this would be to increase this value of k. And the tendency is that when increasing k, you're going to simplify your decision boundary. So here you have a k equals 10, and you have kind of a smoother or simpler decision boundary. You don't have all of those islands. And that means on some of your training data, you're going to misclassify it. But once you look at the global picture, so your other data sets with the same distribution or the actual data that you're going to be using this algorithm for, in the end, on average, it's going to be better than having a very complex decision boundary. So this is kind of the trade-off that you have to play with. And this is more or less so the way your error on your training data and on your test data evolves as a function of the number of neighbors. So what I mean by training data and test data is that you can have the same distribution of points, but the actual points can be different. And the way you usually test these algorithms is that you have a data set, and you're going to leave out, for example, 10% of that data set for testing. So you can evaluate how good it works on points that weren't used for training the algorithm. And so if you train different versions of this algorithm, or in this case it's k nearest neighbor, so you don't even need to train it. But if you run this algorithm with different number of k, with k equals 1, you're going to have 0 error. So you're just going to memorize your data. But once you look at a different distribution, you're going to have a big predictive error in there. So if you increase k, you're going to start to misclassify samples on your training data, but actually your testing data is, or your prediction power on the testing data is going to increase. And there's usually like a sweet spot. So if you have a k value that's too large, you might have a model that's too simple, or the decision boundary is too simple to actually capture the nuances in the distribution. So there's kind of a sweet spot where this algorithm will work perfectly. And usually the way you find this is just by trying different values and see which ones have the best accuracy in the testing data. Sorry. So this trade-off with the k value. It's not just specific to the k nearest neighbors algorithm. It's actually a very general concept all across machine learning, and it's called the bias-variance trade-off. So it's basically the trade-off where, as you increase the model complexity, in this case the model complexity is related to the complexity of your decision boundary, you're going to be increasing it's called the variance because when you look at different data sets, your predictions are going to be, or the error in your predictions is going to be larger. So this error is called the variance. And so as you increase the model complexity, the variance on your predictions is going to increase. But your bias is going to decrease, and this means that you're actually going to get closer to the actual relationship that you're trying to model, or the actual decision boundary. And so you kind of have this sweet spot for a lot of different kinds of algorithms. So if it's regression, if it's a linear regression, for example, it might be too simple for certain kinds of data. So if your data follows a parabola and you try to fit a line to it, it's not going to fit. In this case, we call that underfitting. On the other hand, if you have a model that's too complex, like a neural network, for example, and you try to fit it to simple data, you're going to be overfitting it. And so once again, once you look at a testing distribution where your points might be slightly in a different place, your error is actually going to be larger than the training error. And so there's this sweet spot in the middle where you find a model that actually explains your data, and that's generalizable. So that's the key concept here. You want to find a level of complexity of your model where it generalizes well to new data. Any questions regarding this, by the way? This is a very important concept. You're going to be looking at it like every time you touch a machine learning algorithm, you're going to have to think about this. All right.
Can you share an example of how we take some specific data from, I don't know, like the results of baseball games and take that information into this kind of algorithm? Something like that?
Let's take that example of baseball game. So, for example, yeah, you might create a model where you look at all possible stats of all different players, and stats in terms of maybe historical like averages or whatever, and you try to predict their future performance from that. You might train a model that is capable of reproducing exactly the scores that they had historically from your data set. But if it predicts them to the point where it's basically memorized them, once you get into a new regime, like the future, since it hasn't memorized the future, like it's just going to start predicting. It's not going to be robust. It's not going to generalize. If you have a simple model that just looks at the very like big picture evolution of the player's performance and not at like individual games, it's going to be much more capable of finding a trend and actually continue that trend into the future to predict the future performance. So yeah, in this sense, your model is going to be able to generalize better because it's simpler. Is that clear? All right. Yeah, Moneyball. Any more questions? All right. You have one?
Yeah, just a general question. Like, it's been a while since I've taken stat courses, but so like for like linear regression, I think you alluded to it. Like, if the moments change, like you go to different regimes, then the linear regression breaks down.
Mm-hmm.
Is it the same for like the nearest neighbors, like some of like these like looser ones that are not done like classifying rather than?
Mm-hmm. Yeah, it's kind of the same as what we saw before. In the case of k-nearest neighbors, if you have like this very complex decision boundary, it's basically memorizing all the points. So it's, for example, this whole region, it's thinking it should be blue, but it's just because this point is way outside where it should be. So this is kind of an outlier, like it's out of regime, let's say, but you're memorizing it and you're learning from it. And so in this case, your model is not robust, or it's just learning noise from these outliers. And once you have a different data set, this is not a good example, or in this case, all the data sets are the same, but let's say here you have these different data sets. So for example, this is our training data. And you see, like, there's this bunch of yellow points here. And with a k of 1, you're going to learn that this whole region should be yellow. But then once you get, once you go to your testing data, there's actually like a purple or blue point here. And it's going to be misclassified because your model learned that this region should be yellow. And it's actually, you can look at it in actually when you have outliers from your yellow. So let's say there's a yellow point in there in the middle. You're gonna learn that this region in the middle should be yellow, when in fact it's way inside what should be a blue region. So just the fact that you have this very complex decision boundary is going to induce error once you go to the testing distribution. Yeah.
I don't know if this makes sense even, but what I'm hearing is kind of, in order to be able to predict and generalize, we need to take out the outliers, then the extremes. Yeah. So, I mean, in terms of like, in general, speaking with AI, wouldn't that make predictions, how can I say, like go to the obvious?
But that's kind of the goal.
Yeah, but at the same time, like a lot of innovations have come from the outliers, isn't it? So what does that imply for the model in terms of asking difficult questions?
I think this concept of like the innovation coming from the outliers, I think it's taking this thing a little bit out of context.
Yes.
So, but what you said before makes sense. So, in machine learning, you're kind of always looking for the most obvious relationships, because if you look for non-obvious relationships, they might be noise. And so your model doesn't generalize. The way you have a model generalize is like actually just look at the obvious, or try to find the obvious relationships there. It's like here, like if you want a model that generalizes, the obvious relationship is a parabola. So that's probably your best model choice. All right. One question? Yeah.
It also applies to like LLMs and more complex models, like they can change the temperature of the loan to get more creative, more out of the box results. But I think that is not
Yeah, in that the temperature of an LLM, that's more on the inference part of it. So it's true that like setting a higher temperature, you're going to get like more random results, but that's just a feature of the way the inference works on these kind of models.
Instead of getting the obvious first result, you get the top 10 and you get the top 1. Yeah.
Exactly. But this temperature isn't used during the training of these large language models. So this is like what I'm showing here, this bias variance trade-off applies like to training machine learning models. And yeah, this concept of temperature, it's also very interesting. It might be related in some way, but it's kind of a different thing. Yeah. But great question. All right, any more? Let's move on then. Okay, so we looked at logistic classifiers. We looked at the k-nearest neighbors. Another very used classification algorithm, it's called decision trees. So by themselves, they're not used a lot of times because they tend to produce these squared decision boundaries. But we'll look a little bit later that once you start combining them, they're actually very powerful. But first, let's look at just a single decision tree. So the way these decision trees classify data or train on a data set is by splitting the data set always on one coordinate. So they pick one coordinate, they split it. This creates two branches in a tree. And then for each of those branches, you repeat the process. You can pick another variable or even the same variable, and then you create more branches. And so in the end, you end up creating this kind of decision tree. And so once you want to classify a new example, you go through the branches of the decision tree. And so for example, here, let's say we want to find like the value of a point, let's say here. So the way we built the decision tree, the first cut was on this y-axis. So we see if it's lower or higher than this value, and it's going to be higher. So if it's higher, we should move this way. And then we look at the x value, and we did a cut here. So we see if this point here is to the left or to the right of this boundary. And in this case, it's going to be to the right. And so you go here. And so in the end, the decision, what you save on this tree is just the most common class in this region. So since the most common class in this region is the red triangles, this is going to be classified as a red triangle. And so you end up having this kind of squared decision boundary when you build these trees. And the way we build them, or so the way we pick a variable and then pick where to split it, is you can have several criteria. One of the most common ones is called the Gini index. You might have heard this Gini index to like measure inequality across countries, but it can also be used like to create decision trees. You can also use concepts like the cross entropy, and it produces similar results. This is just one possible choice. And so in this case, this Gini index, you're going to look at the counts, or the actual, instead of the counts, it's going to be the proportion of the points on each side of your decision. So let's say you do this cut, and then you're going to calculate a Gini index for each of the sides. And that's going to be based on how many blue points you have in respect to the total, how many and how many like red points you're gonna have in respect to the total. They should add up to 1 because you're looking at the ratios, and same thing on the bottom. And what you want to do is to split it in a way where you get the biggest increase in the total sum of the Gini indices for each of the regions. And so let's take a look at an example for this. So let's say we have this like simple data set. So you're trying to predict based on the age and the income of a person whether the person buys a computer or not. And you have like different samples for 8 different people with different ages, incomes, and you have your target value, which is called buys computer. And that can either be a yes or a no, so it's a classification problem. So the way we want to construct a decision tree, and so we have to pick which variable we're gonna split across first, and also where we're going to do that cut. So for that we use this Gini, it's called Gini impurity. You can call it Gini index, whatever. And so you first have to calculate it like in the baseline. So without any cuts, we have 4 yeses and 4 nos. So the probability of a yes is 0.5 and the probability of no is 0.5. And then if you use that formula, you're going to have 1 minus 0.5 square plus 0.5 square, all brackets. So 1 minus 0.25 on 25, so you get like 0.5. So that's your baseline Gini impurity. And then the way you pick a cut of the data set is that after a split, we're going to have to calculate it for all the variables and for all the possible splits. But for each of them, we calculate a weighted sum of the Gini indices for each of the splits. And so once you have this weighted sum, you compare it to or you subtract the original Gini, and that gives you the gain in the Gini impurity. And so we're going to choose the cut that has the largest gain in Gini impurity. So let's take a look at an example. So let's I don't have the image there. Let's say we decide to do this cut on the income variable, and we decide to do it at 45K. So this kind of seems like when you run this algorithm, it's all automated. It's going to try all different possibilities. But you can kind of have a sense that if you want to split this data set and build a decision tree, possibly a best cut would be somewhere here. So let's run the example with that. So if you have the cut there, and you take a look at an income lower than that, you're going to have 0 yeses and 3 nos. So if you run that through that formula, you have 1 minus 0 over 3 squared, which is 0, minus 3 over 3 squared, which is 1. So since there's no impurity there, your Gini impurity is going to be 0. Because all of the classification here, all of the output variables here have the same class. And then we look at the top part. And so we have this might have been okay, no, these are the people. Yes, 3. This might be a ChatGPT error, I'm sorry. But yeah, you have like, if you look at the cut above, you should have 4 yeses and 1 no. So this number of yeses should be 4. Okay, it's correct here. Yeah, I should have read this better when I come up with an example, but this is correct. Okay, so you have 4 yeses and 1 no. And so you get the probabilities here, so 0.8 and 0.2. And you can calculate the Gini index from that, and you get 0.32. So that's for the top part, and we have 0 for the bottom part. So now we weight the Gini indices according to the number of samples in each of the regions. So since on the bottom we have 3 samples, we're going to multiply this by 3 over 8, which is the total. And so you multiply 3 over 8 by the 0, which is your impurity on the bottom. And then you add 5/8, which is the 5 samples out of the 8. And you multiply this by the Gini index on the top part. And that gives you the final Gini after the split. And so in this case, your Gini gain is going to be your original one minus the Gini after the split, because in the end what you're actually trying to do is minimize the impurity. So we want to choose the value, or so we subtract this here. So we want to have or pick the cut that minimizes this value, so it maximizes this final value here, the Gini gain. So this is for one cut, which we picked sort of randomly, but when you run this in a decision tree training library, it's going to try out all of the cuts. There might be some optimizations there, so you don't need to do all of them, but in this case, I've run all of them, and we see all of the Gini gains for all of the possible cuts here. If you want, feel free to go through the math for all of them to check it, but it should be okay if we trust ChatGPT. And so you look at all of the cuts, and you see that actually the one we chose was actually the most reasonable one. It has the biggest value for the Gini gain, and so it has the lowest value for the final weighted Gini impurity after the cut. And so that's the first cut that we're going to do. And so yeah, if you can do that first cut there, and then you continue running the algorithm. So here at the bottom you already have 0 impurity, so we can stop. But at the top we still have some impurities, so we do another cut, and you find that if you run the whole process again for both variables and for all possible cuts, you find that this one is the one that gives you the the best result. So in the end, you perfectly classify the sample, so you reduce the impurity to 0. And this is how you train a decision tree. So once again, for decision trees, there's a way to tune them and to play with this bias variance trade-off. And so one way would be to set a maximum depth for the trees. So we could say, in our previous example, that we actually have a maximum depth of 1 and we're just splitting a variable, so we never do that final cut. And so we end up with some impurity at the end, but that means that we haven't memorized the data set and that we have a simpler model. And that simpler model might actually be able to generalize better on testing data. And so, yeah, if you pick different numbers of maximum depths, so if you just have 1, you're just going to split the data on 1 variable. If you have 2, you can have like deeper or a more complex boundary. Then 3 and 4, you get increasingly complex decision boundaries. But it might get to a point where it's too complex. In this case, no, because you have a lot of samples. But if you try to run a full decision tree on all of this data and try to classify it perfectly, you might end up with a very jagged decision boundary that then doesn't generalize well to the testing data. And yeah, any questions regarding decision trees? Also, are we on time? Okay, we have maybe 5 more minutes, so it's not a problem. I'm going to, let me check how many slides I have left.
Can you share next your presentation in Discord?
I've shared it on Discord. It's on the announcements channel. Yeah, because the font here is a bit small, so it's better if you follow it from your computers. Okay, I have a few more slides left. But yeah, maybe we'll stop here. If you have any questions, feel free to ask any final questions, and we'll do the rest of the classification class tomorrow. Is that it? Okay, awesome. Let's get some coffee again. Thank you.